In this video, I'm going to give some examples of using the derivative of the natural logarithm. So first of all, here's the derivative rule for the natural logarithm. I'm not going to be able to derive this in this class, at least not easily, so I will just have to tell you what it is, and you'll just have to trust me. The derivative of the natural logarithm is the reciprocal. Since we almost always are dealing with the logarithm of some more complicated expression, you almost always see the derivative of the logarithm in conjunction with the chain rule. So that's why I've written it this way. The derivative with respect to x of ln of stuff is 1 over the stuff times the derivative of the stuff. A couple of things to watch for. There is no matching ln here. The derivative of ln, there's the 1 over the stuff that the ln is applied to, but the ln itself is transformed into this reciprocal. Second thing, it's also not 1 over the derivative of the stuff. That's because you multiply by the derivative of the stuff and you apply the 1 over to the original stuff. That's the chain rule. I can give you just a hint of why this function is so important. Here on the right side of the slide, I've written out several instances of the power rule. If you'll notice, the derivative of x cubed has an x squared in it. The derivative of x squared has an x to the first in it. The derivative of x to the first has, well, it's a constant, x to the 0. And then the derivative of x to the minus 1 has an x to the minus 2 in it. What that means is that from the power rule, it's not possible to construct a function whose derivative is just power minus 1. So one of the mysteries that was solved once the logarithm function was developed was now we have a function whose derivative is x to the minus 1. And so what you're seeing, that's what you're seeing right here. Let's do some examples of this. So here's our first example. Suppose f of x is ln of 3 times x, and we're just going to ask for the derivative. Okay, so there it is. I'm going to write the derivative rule over here to the side. Derivative with respect to x of ln, I'll write it out in words. Ln of stuff is 1 over the stuff times the derivative of the stuff. Okay, so looking at this equation, f of x equals ln of 3 times x, first thing to notice is the ln is the outermost operation. Let me make that clear here as well. I'm going to write f prime of x is, well, just the derivative with respect to x of its formula. If you look, if I want to match this up against the rule for the derivative of ln, I've got derivative of ln of stuff is reciprocal of stuff, so 1 over the stuff, times the derivative of the stuff. So the stuff matches up with 3 times x. Okay, so now I need to apply this rule. I need 1 over the stuff, so 1 over 3 times x, and then let me make this a little clearer here. 1 over the stuff goes there, and I will multiply by the derivative d over dx of 3 times x. So as you can see, the ln does not appear on the right-hand side. It has been transformed into reciprocal because the derivative of ln is reciprocal. There's one unfinished derivative step, and that is here, the derivative of 3x is 3. Now we're finished with the derivative operations, and all that's left is to clean up a little bit. If you notice, we have a bunch of multiplication and division. I can put the 3 over 1 and cancel the factor of 3 from top and bottom, leaving just 1 over x. So that is first example of using the derivative rule for the natural logarithm. Now let me show you another way to do this problem. Okay, here we go. Another way. I'm going to return to f of x, and this time I'm going to take apart. So this is an algebra step. There's no derivative yet. If you'll notice, ln is applied to multiplication. And remember that ln of multiplication can be taken apart. The result is ln of the left, which is 3, plus ln of the right, which is x. So that is a step of just algebra. Now we can take the derivative First, I'll just write that f prime of x is d over dx of the formula for f. We have derivative applied to addition. And we do this so often we don't even write it down anymore. But just to be extra clear about this, the derivative of that thing, ln of 3, plus ln of x is the derivative of the ln of 3 plus derivative of ln of x. Now think about this for a minute. What is the derivative of ln of 3? It is 0. The reason for that is that ln of 3 is a constant. In fact, if you put it into your calculator, ln of 3 is about 1.1. It's a constant. And remember that the derivative of just a constant is 0. Now what about the derivative of ln of x? It's the reciprocal of x, so 1 over x. Now, if you wanted to continue with the chain rule, you would just multiply by 1, so we don't usually bother writing that. But there you go. So now we clean this up, and we get that f prime of x is 1 over x, which is the same thing that we got doing it this way. That was using the formula directly and then doing some algebra to clean it up. This was doing some algebra to take apart the formula first, then applying the derivative rules. So you can see the derivative rule for ln is consistent with its algebraic properties. All of the derivative rules for all functions are consistent with algebra. That's why they are the way that they are. Okay, so there you go. First example of a derivative involving ln. Let's do another one. This function, g of t equals ln of a t squared plus bt plus c. Now, just to make sure that all of this is clear, the intention for this problem is that a, b, and c are constants. In fact, let me color code them. I usually use bright blue to indicate that they are frozen. Now, as to why would I have a function like this? Well, sometimes you're dealing with constants that are, clumsy decimal numbers. It may be that a, for example, is 2.86053, and b is negative 1.02 times 10 to the negative third, and c is 6.86 times 10 to the negative fifth. And writing that over and over and over again is error prone and tedious, and so sometimes you'll see a formula where you just write a, b, and c as constants. Particularly when you're dealing with physics, for example. Physics is full of physical constants, such as the Earth's gravity constant, which is 9.8 meters per second squared. And just rather than writing those quantities out over and over again, we'll reduce them to just a single letter and write that. And then when we need to calculate, we can just remember what the constant is. Okay. I'll begin by writing that g prime of t is the derivative with respect to t of its formula. Okay, the derivative is applied to this expression, and the outermost operation is that logarithm. So once again, we need to write, well, you don't have to write this out every time, but let me do so just because this is our first lesson on this derivative. This time I'll use d dt because our variable is t, independent variable is t. Derivative of ln of stuff is 1 over stuff times the derivative of the stuff. So the first step in writing out g prime and working on that derivative is to apply this rule, and the stuff is this at squared plus bt plus c. Okay, so following this rule, I'm going to write 1 over this stuff, at squared plus bt plus c, and then multiply by the derivative of that same stuff, a t squared plus bt plus c. So that's applying the rule for the logarithm, the derivative of the logarithm. Now, to give just an extra bit of explanation for this, think for a minute, what would the derivative of 5t squared plus 7t plus 3 be? Okay, let me do it out. 5 times 2t plus 7 times 1 plus 0. And usually we do a lot of this algebraic cleanup in our heads and just jump straight to 10t plus 7. But if you look at what we did, when you do the derivative of a sum of pieces, remember you do the derivative of each piece and then add and subtract the pieces back together. So that's what you're seeing here. For the plus 3, Since 3 is a constant, its derivative is 0. For the derivative of 7t, we keep multiplication by 7. So 7 is a constant, but it multiplies the t. We keep 7 times in the derivative. And then for 5t squared, we keep the multiplication by 5 and apply the power rule to t squared to get 2t. I'm going to do the same thing over here, but instead of 5, 7, and 3, I have a, b, and c. Okay, so here we go. G prime of t equals, I'll leave the part that we've already done unchanged, at squared plus bt plus c. Oh, that's ugly. bt plus c times, I'm going to go term by term. For derivative of at squared, I keep a times and multiply by the result of the power rule applied to that t squared, which is 2t. And that is parallel to that. For bt, which will be parallel to the 7t over there, the derivative of that is b times 1. We keep multiplication by b. And finally, the derivative of plus c is parallel to the derivative of the plus 3 over here. So that gives us plus 0. Having done that, we can now clean things up. And I'm going to put in some extra parentheses just to make everything clear. So there it is. The first part is 1 over the stuff, at squared plus bt plus c, times the derivative of the stuff, 2at plus b. Very often you will see all of this put together into a single fraction. That gives 2at plus b over a t squared plus bt plus c. So there you go. That is the derivative of ln of at squared plus bt plus c. Let's work another example. This one is one of these tongue twisters that you sometimes get in mathematics. You'll see what I mean when we work this out. We're going to look at h of z equals ln of z. And do the derivative. Here's where you got to keep your thinking caps on. Take a minute, try this out, and see what you can come up with. Okay, what I've written here is that if h is ln of z, then h prime is the derivative of ln of z. Since the natural logarithm is that outermost operation, I'm going to use the same rule. I've written it here using z because the independent variable is z. And in this case, the stuff is this ln of z that's on the inside. So this is a sort of funny looking formula because it's a composition of two functions, both of which are ln. Yeah, so you got to be really careful how you do this. So the first step is, I need some more room here, h prime of z equals, I need 1 over the stuff, and the stuff is that ln of z on the inside. The first ln has turned into reciprocal. Then I continue with this chain rule factor, derivative with respect to z, again, of the stuff, which is that inside ln of z. So again, the first ln, the derivative of that has given us this reciprocal. So the first ln is gone. The second ln does appear right here. Its derivative will appear here in this chain rule term. Let me copy the part that we're finished with. And now the derivative of ln of z, what do you think that is? That's 1 over z. Now, just like I said, this is a little bit of a brain bender. Can you see how to clean this up? We'll just multiply the two fractions together. And for reasons that I think are just purely because it looks better, it's traditional to put the multiplication by z on the left in something like this. So there you go. Derivative of ln of z is actually 1 over ln of z times z, like that. Now let's do one more. Oops, that one. So this is u equals x squared times ln of x. Couple of things about this one. First, there is an ln in it. But is ln the outermost operation? Actually, it isn't. You have to be careful not to jump the gun, not to panic. The derivative of u is the derivative with respect to x of its formula. If you go through and, oops, I left out the e, p, f, e, m, d, a, s. So this function application happens early. The exponent happens early. The last outermost operation is that multiplication, which means we need the product rule to start with. Take a moment and work out the product rule for this derivative. Okay, the left is x squared. The derivative of the left is 2x. The right is ln of x. Now this is something we just covered. What is the derivative of ln of x? 1 over x. Now we need to use the product rule to put all of that back together. Okay, du over dx. Remember the product rule, derivative of the left times a copy of the right. So 2x times ln of x plus copy of the left times the derivative of the right. X squared times 1 over x. Okay, take a look at that. It is possible to do a little bit of cleanup. So du over dx equals, for this group, just in front of the addition, there's not much we can do other than drop some unneeded parentheses. For the group after the addition, we can actually simplify a little bit. There's a factor of x that we can cancel. So I can cancel an x like that, and that will leave us, instead of x squared times 1 over x, that will leave us with just x. So there you go. That's the derivative of x squared times ln of x.